Understanding this electrophilic addition mechanism helps us to understand why Markovnikov's rule is true. So if we look here, adding hydrochloric acid to propene, the product is actually going to be determined by the first step. So the hydrogen adds first. The hydrogen ion adds first. It could add to carbon number 2 and form this if it adds to carbon number 1, then the positive ion, the positive charge is on the other carbon. We get an isopropyl cation. If the hydrogen adds to carbon number 2, then we get the positive charge on carbon number 1. Because when this attacks the double bond, it's going to be bonded to either carbon 1 or carbon 2. And what we find is that this addition to the second carbon, the middle carbon, doesn't happen. And that's consistent with Markovnikov's rule, because this hydrogen is going to add to the carbon that has more hydrogens. The question is, why? It has to do with the stability of the carbocation. And the stability is going to depend on how many R groups are attached to that carbon. So this is a tertiary carbocation. Tertiary meaning it has 3 R groups. These R groups are any alkyl group, carbons and hydrogens. So these could be methyl or ethyl or propyl or anything like that. This is called a tertiary, and this is more stable than this one, which is a secondary. It's got 2 R groups. A primary carbocation has 1 R group, and if it has no R groups, it's going to be a methyl carbocation. And this is not given a primary, secondary kind of thing because it's unique. It's the only one. But this is going to be the least stable. What stabilizes the carbocation is when that positive charge can spread out. We call that delocalization. When it can spread out over several atoms. Alkyl groups are going to stabilize the carbocations by donating electron density from carbon-hydrogen and carbon-carbon sigma bonds that can line up with the empty p orbital. So if the carbocation is here on this carbon is attached to 1 alkyl group. Is this primary, secondary, or tertiary? How many R groups are attached to this carbon? How many other carbon atoms? Just 1. Here we have 1 R group. It's a methyl group. So this is a primary carbocation. These hydrogens are not going to help at all with this positive charge. But this neighboring carbon has an sp3 hybrid orbital here that's overlapping with a hydrogen atom. And there's electron density here. And so it can kind of share the electron density with this empty p orbital, and that makes things a little more stable. The more carbon atoms you have attached, let's just draw in another one. So if we had another carbon atom over here that was overlapping with a hydrogen, we'd have to get rid of one of those. Now we've got this carbon-hydrogen bond and this carbon-hydrogen bond. They both have electron density, and they can share their electron density with this empty p orbital, and that makes things a little more stable. And if you have 3 carbons attached here, then it becomes even more stable. So the electrophilic addition of the unsymmetric reagent to the unsymmetric double bond is going to proceed in a way as to involve the most stable carbocation. So let's look at what happens here. Asking for the steps in the electrophilic addition and showing that the reaction occurs via the more stable carbocation. So here they're actually giving us the product that's observed, and this is the product that's not observed, and we're just trying to figure out how to show what's going on there. So here we have the hydrogen. This is the more electropositive of these two. So the hydrogen is the electrophile. It's going to attack this double bond. We've got two possibilities when it does that. So we get rid of the double bond. We could put the hydrogen over here. If the hydrogen goes to this carbon, then where does the positive charge go? It goes to the other carbon in the double bond. So this one's going to have a positive charge. If this hydrogen adds to this carbon, then the other carbon is going to have the positive charge. That's the first step in the addition, is that the hydrogen ion attacks the pi bond, and then we get a carbocation formed on the other carbon atom. Does that make sense? Which of these carbocations is more stable? Which of these carbon atoms has more carbon atoms bonded to it? How many carbon atoms are bonded to this carbon atom right here? 1, 2, 3. Right? So this is a tertiary, and this one is secondary. Right? This carbon on the corner here is bonded to this carbon in the ring and this carbon in the ring. It has 2 carbons. So carbon does not like to have a positive charge. When a carbon has other carbon atoms next to it, they can help it stand this positive charge by sharing their electron density. It's just like when we're having a hard time, we like to have friends around us that help us bear our burdens, right? They're like, yeah, this is really hard for you, but I'm going to help you, I'm going to support you. So that's one way maybe that will make sense. This carbon atom here has 1, 2, 3 friends around him that can help him out with this positive charge that he doesn't like having. This carbon only has 2 friends. And so this is going to be much more unstable. And so this is not likely to form. The next step that would happen then is that the iodine will add where the positive charge is. Because this electron, this hydrogen, okay. So we've got the hydrogen hydrogen ion going over there, and then we've got the iodide ion left. And the iodide is either going to go here or here, depending on which of these we made. This one's more stable, and so this is the one that we're going to have happen. This is what we will observe, and we see that the iodine goes to that carbon, the one with the methyl group on it. We do not see this product forming. And the reason is because the carbocation is not very stable. The more stable carbocation will be formed. Any questions? This is a lot to absorb, isn't it? Yes?
It looks like the carbon that you're talking about is bonded to 3 carbons each in both of those strings.
This one is bonded to 3 carbons. 1, 2, 3. This one is only bonded to 2. 1, 2. Let's try drawing the ring out. So if we're looking at this guy, He's got 1, 2, 3 other carbons bonded directly to him. If we look at this guy, he only has 2 carbons. 1, 2. So he's got 2 neighboring carbon atoms to help bear the positive charge. But this guy has 3, and so he's more able to have a positive charge. And that's why this carbocation is more stable, and this one will be formed, and this one will not. Does that make sense?
Okay, yeah.
I can see it in my mind, but getting you to see it in your mind is challenging. And I can't know that you're not getting it unless you ask me questions.
I think what's confusing was the double bond.
What happened with the double bond?
Yeah, because you don't have the hydrogen ion, the hydrogen cation. If you're, is the drawing right there in the lower right is the first one right there? Yeah.
This one?
The double bond's supposed to be right there.
The double bond was here. So let's try starting this all over. And let's put, here's our hydrogen ion. That's our electrophile. And this is electrophilic attack. And so what happens is, let's maybe use purple here, is that these electrons in the double bond, that arrow with 2 heads, means that both of the electrons in the double bond come up here to make a bond with this hydrogen ion. That leaves a positive charge over here. And then we've got, this is going to be a positive charge here. Because this carbon right here has 1, 2, 3 bonds. It only has 3 bonds. It's missing an electron, so it's a positive ion. What happened to its electron? Well, its electron that it was sharing in this pi bond, bless you, went up here to form this single sigma bond here. So both of the electrons in the pi bond, the second line there, swung up to make a bond with the hydrogen. Whichever one the pi bond goes to form a bond with the hydrogen, then the cation is on the other carbon, because that carbon lost its electron. Does that make sense? This carbon can handle it better because it's got 3 friends around it. Any other questions? Yeah, I was like, that's supposed to be a new section. Yeah, there it is. It is a new section.